When people hear Raspberry Pi, they think of tiny single-board computers running full Linux operating systems. But Raspberry Pi also makes microcontrollers, and this one right here is the Raspberry Pi Pico 2. If you're interested in computer architecture and low-level hardware like I am, then this little board here is something special. What makes the Pico 2 particularly fascinating is the chip at its core. Instead of using just one CPU architecture, it contains two completely different ones, an ARM core and a RISC-V core. Both architectures run at the same 150 MHz clock, share the same memory and use the same bus architecture. However, naturally, only one architecture can be active at any given time. That makes this an incredibly interesting platform for comparison. Since both the ARM and RISC-V CPUs are running on identical hardware, we can put them through a number of fun tests and get a fair idea of how they stack up against each other. By the end of this video, we'll have a much better understanding of how capable RISC-V really is when compared to ARM, which is the architecture that has dominated microcontrollers for decades. First, let's take a closer look at the chip, which is the RP2350. Information about both the ARM and RISC-V cores is documented in this datasheet, which can be downloaded from Raspberry Pi's website. One thing I love about Raspberry Pi is that they always have very clean, modern, and well-organized documentation. We can find the information we're looking for in sections 3.7 and 3.8 respectively, which outline the main features of the ARM Cortex-M33 core and the Hazard3 RISC-V core. Let's start by looking at the features of the ARM core. While many of these features are targeted for embedded systems specifically, some of them are more interesting for our benchmarking purposes. For example, the Pi Pico 2 implements the floating point unit and the digital signal processing or DSP extensions. If you aren't aware, microchip companies like ARM will often license their designs in a very modular fashion. They will sell a base design and charge more for added features or extensions, as they like to call it, such as the FPU and DSP. This is because not every application of the core will require these features, and they can come with drawbacks of their own, aside from added cost, such as their increased power consumption. The full details of this core can be found on ARM's website. On the other hand, the RISC-V core is the open source Hazard3 core, made by engineer Luke Wren at Raspberry Pi. If it's not clear yet how fascinating this is an actual full 3-stage pipelined open source processor, which you can view the code of on GitHub under an Apache 2.0 license. If you really wanted to, you could even download this design and run it on your own FPGA. The philosophy of RISC-V is taking the modular approach I described earlier and turning it to 100. The base 32-bit instruction set called the RV32I is quite small. Extensions are then added on top of them. However, notably, the Hazard3 core lacks the FPU and DSP support, which means floating point and multiply accumulate operations will take multiple cycles instead of one hardware cycle on the ARM core. However, it does include some cool instructions, such as this bit manipulation for scalar cryptography. Before moving on to some code benchmarks, it's important to take a step back and understand why Raspberry chose to include both cores to begin with. As far as I understand, Raspberry Pi including both architectures on the Pico 2 to provide developers with a stable RISC-free environment to experiment with RISC-V. By placing the open source Hazard3 core on the exact same chip as the standard ARM core, engineers can confidently test their code and simply switch back to the ARM cores at boot time if they run into any issues. Beyond offering a safe testing ground, this dual-core approach champions open source education by popularizing Hazard3 as a clean production-grade core that students, researchers, and hobbyists can study, just as I am doing in this video. Having said that, let's run some fun benchmarks. I decided to run 3 benchmarks, one comparing a single precision floating point calculation, one for a double precision floating point calculation, and one for an integer calculation. I used the Mandelbrot for the floating point tests and the prime numbers algorithms for the integer tests. Going off the datasheets, we could hypothesize that the single precision FPU unit on the ARM core will allow it to outclass the RISC-V core on this task. However, they might both struggle with the double precision workload. We could also hypothesize that the integer workload would be comparable between the two, as the ARM core doesn't have any inherent advantages on that front as far as I know. Looking at the results, it seems our hypothesis holds true, and the RISC-V core actually surprisingly beats the ARM core on the integer task, even though it's only a small margin. I hope you enjoyed this comparison of the two architectures on the Raspberry Pi Pico 2. Needless to say, the benchmarks I employed don't exactly represent embedded systems workloads, so they shouldn't be taken as definitive measures of performance. Even so, I think the results are incredibly impressive. The fact that an open source processor core whose entire design can be easily downloaded, studied, and modified can go head to head with one of the most widely deployed commercial microcontroller architectures is a testament to how far RISC-V has come. The Pico 2 offers a unique opportunity to explore both of these on exactly the same silicon. I might explore the Hazard 3 RISC-V core further in the future by running more extensive or realistic benchmarks, since I find this core really fascinating to work with.